Good evening, everyone. Myself, Gautam Sharma. I welcome you all in behalf of Sapience Education. So today I am going to solve question number 10.11 for the chapter of thermal properties of the matter. So let us read the question. In 10.11, they are asking the coefficient of the volume of expansion of the glycerin is this 49 into 10 power minus 5. What is the fractional changes in its density for 30 degree Celsius rise in the temperature? So basically, they have given alpha B or gamma. We can also say alpha B, that is volumetric expansion coefficient of volumetric expansion. So this is equal to 49 into 10 to the minus 5 Kelvin inverse. Okay, and let us consider this is the mass of the glycerin, and this is the volume of the glycerin. Basically, they are asking that if we change the temperature, so what will happen? It will expand. So definitely density will decrease. So what is the fractional changes in the density? That is delta rho by rho. We want this quantity is equal to how much? Before that, we need to understand that as we know that mass is equal to density into volume. So mass is constant, right? So if you know that partial differentiation, so I hope you have understood dm is equal to rho into dv plus v into d rho, and this is equal to 0. Why 0? Because mass will remain constant. Whenever you will apply or increase the temperature, so the mass will remain constant. So finally, from here we can write here rho into dv is equal to minus v into d rho. So from here dv by v is equal to minus rho by minus d rho by rho. So in place of a d rho by rho, or we can also write minus delta rho by rho. So in place of this, we can write also dv by dv only. So basically, if you want to find the dv by v, then we can easily find out. Okay. Now, as we know, one of the most famous formula, that is change in volume is equal to original volume into volumetric expansion into delta T. So change in volume by V naught, this will be equal to alpha V into delta T. So this can be also written as minus delta rho rho by rho. So from here we can find delta rho by rho. So if we have a value of a delta rho by rho, so let us find that rho b. Rho b is given as 49 into 10 to the power minus 5 Kelvin inverse into rise in the temperature is how much? Delta T is 30 degree Celsius or 30 Kelvin. So when we multiply it, so we will get minus 0.010147. So this is delta rho by rho. Okay. So I hope you have understood this, and this delta rho is the this is known as the fractional change in a density. I hope you have understood now. Now let us do question number 10.12. A 10 kilowatt drilling machine is used to drill a bore in a small aluminum blocks of a mass 8 kg. How much is the rise in the temperature of the block in a 2.5 meter, assuming 50% of power is used above heating the machine itself, or lost to the surrounding? Specific heat of the aluminum is 0.91 joule per gram per Kelvin. So actually what we need to find a specific heat. We need to find out how much is the rise in temperature. So we want delta T, okay? So they are applying, what happens, there is a drilling machine. So what happens when it rotates with the power is given. So due to this power, there will be a heat generation, okay? And due to heat generation, there will be temperature difference will be created or rise in a temperature will happen. Rising, rise of temperature will happen, okay? Got it? Now what we need to do? First of all, heat released, heat given, or heat lost, or we can say that the heat given by the machine is equal to heat absorbed by aluminum. Okay. So heat energy. So heat is equal to how much? This will be power into time into efficiency. Okay. And this will be equal to a mass into specific heat of the aluminum into delta T. Now what we want to find? We want to find delta T. So for delta T, so delta T will be equal to power into time T into efficiency divided by mass into specific heat. Now the power is 10 kilowatts. So 10 kilowatt means what? 10,000 watt into time. Time, they have given time as 25 minute, 2.5 minute. So this will be 2.5 into 60 second only. So this will be 2.5 into 60 into efficiency. Efficiency is 50% means what? 0.5 divided by mass. What is the mass of the aluminum? Mass of the aluminum is how much? Aluminum block is 8 kg mass. And what is the specific heat of the aluminum? So specific heat of the aluminum is given as 0.91 joule per gram per Kelvin. So I want joule per kg Kelvin as a standard unit. So we have to multiply it by 1000. 0.91 into if we will multiply it by 1000, so in thousands, so then only it will get converted into joule per kg Kelvin. So this is very simple. So put here 910 joule per kg Kelvin. Now from here, if we calculate, so how much we will get? We will get approximately equal to 103 Kelvin or 103 degree Celsius is the change in temperature. So I hope you have understood this solution. So if any query, please comment. Thank you for now let us discuss question number 10.13. A copper block of a mass 2.5 kg heated in the furnace to a temperature of 500 degrees Celsius and then placed on a large ice block. What is the maximum amount of ice that can melt? Specific heat of the copper is given and heat of the fusion for the water is given. Now let us see that what there is a copper block, okay, and its mass is how much? 2.5 kg and heated to a furnace of 500 degrees Celsius. So the temperature is 500 degrees Celsius. And then it is placed on a large block of the ice. So this is the larger block of the ice. Okay, we don't know the mass. We want to find the mass. Okay, so it will be, we want to find the mass of the ice block which melts. Okay, so which melts. So from here we can also infer that the heat lost by copper is equal to heat gain by ice. So heat lost is how much? So this will be Q is equal to MST, that is mass of the copper, into specific heat of the copper, S into delta T. So delta T is here 500 minus 0 because it will ultimately come into 0. So heat gain by the ice. So heat gain, say ice gets converted into ice just melts. So it means that it requires a latent heat of fusion. So this is mass of the ice into delta LF, latent heat of the fusion. Now specific heat of the copper SCU is given as 0.39 joule per gram Kelvin. I want to standard unit, so we can put here standard unit as a 0.39 into 1000 joule per kg Kelvin. So this will be 390 kg Kelvin, joule per kg Kelvin. Okay. So we have got now the latent heat of the fusion LF for the water is 335 joule per gram, but I want kg. So this will be 33500 joule per kg. So we have got the standard one. So we will put the values. So mass of the copper is how much? So mass of the copper is 2.5 into specific heat of the copper is how much? It is 390 into 500, and this is equal to mass of the ice. We want this only into latent heat of the ice. This is equal to 33500. Not 00, it should be 000 only because we have to multiply it by 1000. Okay. So from here, mass of the ice will be equal to 2.5 into 390 into 500 divided by 33500. So when we do this, so our calculation, as per our calculation, we will get 1455 kg or approximately 1.5 kg of the ice will. So hence 1.5 kg of ice gets ice melts. So I hope you have understood this solution. Now there is next question. In an experiment on the specific heat of the metal, 0.2 kg of a block of a metal at 150 degrees Celsius is dropped in a copper calorimeter of equivalent, that is 0.025 kg, containing 150 centimeter cube of water at 27 degrees Celsius. The final temperature is 40 degree. Compute the specific heat of the metal if heat lost to the surrounding are not negligible. Is your answer greater or smaller? So let us assume before that we need to find the specific heat of the metal. So what actually happening here? It is the case of the totally calorimeter. So this is the calorimeter, and this is made up of a copper. Okay, but it contains a water. So water, how much water it contains? 150 centimeter cube. This is equal to 150 gram, and the copper, which is water equivalent mass of the copper is given as 25 gram. So total mass is how much? Total mass we have got 150 plus 25. So this will be 175 gram. Okay. So the initial temperature of this body is how much? So the initial temperature of this body, T initial, was how much? 27 degrees Celsius. And the T final, after a block when it has been inserted, so the final temperature become 40 degrees Celsius. Okay. Now there is a copper block. So if there is a copper block, so this is the copper block. Okay. And it has some mass. Mass of the copper block is how much? This 0.2 kg. So this will be 200 gram. And its initial temperature is how much? Its initial temperature is 150 degrees Celsius. Final temperature is how much? Here 40 degrees Celsius. Okay, and we want a specific heat of the copper. So basically what we note that heat gain is equal to heat lost. So the heat gain by this heat, it will gain the heat and this will lose the heat. Okay, so heat gain is how much? Heat gain by this bucket is how much? Mass. The mass, we can take a gram both the side. We will take the mass in a gram only, so that it will get cancelled out. So this will be 175 into specific heat of the water is how much? Water, specific heat of the water they have given or not? Compared to the specific heat. Okay, so the specific of heat of the water is 1000 calorie. We can take it as a 1000 calorie into change in temperature, that is equal to 40 minus 27, and this will be equal to heat loss. Heat loss is equal to 200 mass into specific heat is how much? Specific heat of the copper and into change in temperature. So change in temperature is 150 minus 40. So this will be much? The specific heat of the copper is how much? 175 into 1000 divided by, sorry, before that I should multiply. So this will be 13 divided by 200 into 110. So finally we will get 103.41 calorie per kg. If you want the answer specific heat in not calorie but joule, so specific heat of the copper is equal to, specific heat of the copper is equal to 103.4 into 4.2 joule per kg Kelvin. So this will be approximately equal to 434 joule per kg Kelvin. So I hope you have understood this, right? Now the second question they are asking is that if the heat loss in the surrounding are not like negligible, so if heat lost will be not negligible, then what will be the answer? See here again from this this is specific thing is that specific heat of the copper block is equal to heat gain divided by mass into delta T. Okay. See if if we consider if we consider heat loss is heat lost is not negligible, not negligible Jebel, means that heat gain is less. Heat gain is less than actual heat gain. Heat gain. So if heat gain will be less, so what will happen? Is hence it will also become less. So hence specific heat of the copper will have less value than actual values. Okay. So I hope you have understood this question. Uh, Now let us observe the question. It is given below the observation of molar specific heat at a room temperature for some common gases: hydrogen, nitrogen, oxygen, nitric oxide, carbon monoxide, and chlorine. The measured molar specific heat of the gases are markedly different from those of for the monoatomic gas. Typically, molar specific heat for a monoatomic gas is 2.92 calorie per mole Kelvin. Explain this difference. What can you infer from the mm, from somewhat larger extent? See, this is we if we think that monoatomic gas, so what we know about the monoatomic gas, CV for the monoatomic gas. let us know the formula for to find Cv for monoatomic gas. So Cv or a diatomic gas. So this will be equal to F by 2 into R. So the value of R is approximately is equal to 8.147 joule per mole Kelvin. Okay. So this is the value of R. Now for monoatomic gas, for monoatomic gas, degree of freedom is equal to 3 only. So from here we can find Cv. So if we put here 3 by 2 into 8.147 joule per mole Kelvin. So this will be how much? So when we calculate it, so our answer for this will be see if you they have given calorie per mole, so we need to convert R in calorie per mole also. So for R value, R has a R value, so you can get the value of R as 1.98 calorie per mole Kelvin. Okay, so this is the value of R. Okay, now we can, instead of putting in the joule per mole Kelvin, so why don't we put it in the form of a calorie, so that we can easily compare. So we can easily compare. So let us do the same. So this will be 1.98. So when we multiply it, so our value of a CV will be approximately equal to 2.97 calorie per mole. Okay. But when we talk about the diatomic gas, when we talk about the diatomic gas, so degree of freedom, that is value of F is equal to 3 plus 2, that is 3 translation and 2 rotational motion. So degree of freedom is 5. So for diatomic gas, Cb is equal to 5 by 2 into 1.98. So this will be approximately equal to 4.95 calorie per mole. Okay. So when we compare it, so since it is your hydrogen, all are not monoatomic, H2 diatomic, N2 diatomic, O2 diatomic, nitrogen oxide NO diatomic, carbon monoxide diatomic, chlorine Cl2 diatomic, all are diatomic, all are diatomic, diatomic. So see here what we have got 4.95. So it is approximately equal to 4.95, 4.95, 4.95, approximately equal to 4.9. But there is a drastic change in the value of a chlorine. So why this happens? See, you know that chlorine has 3 degree of freedom is equal to 6. 3 translational, 3 translational, 2 rational, and 1 vibrational. So if we put degree of freedom is equal to 6, so Cv is equal to 6 by 2 into 1.98. So this will be approximately equal to, the value will be approximately equal to 5.94. 5.94. So it is 5.94, but still we have large difference, and this difference is due to difference is due to the gas chlorine, due to chlorine, as it is real gas, not a real gas, not an ideal gas. So some may constants will be left. So that's why I hope you have understood and we can compare this. So explain the difference. So difference. So these are the difference. So I hope you have understood. All are diatomic only. Okay. So I hope you have understood this section. So thank you for watching my video.